So now the final part of today's meeting is an address by the Exceptional Lecturer for 22-23. So it's with great pleasure I'd like to introduce Professor Mark Williams, and he's going to give us a lecture on the Anthropocene, planetary scale change. Actually, sorry, I've just lost the title. There we go. Planetary scale change to the biosphere and the future well-being of planet Earth. So over to you, Mark.
Thank you very much, Rachel. And I hope I'm not going to give you, to follow on from Nick, an example of ecosystem engineering in shallow time that is not going so well at present for the biosphere on planet Earth, but we'll see at the end of this presentation. So I'll just share my screen. And hopefully you can see that now. That's great. And just also to thank the Society for giving me the opportunity to give this talk. It's quite topical at the moment because the Anthropocene Working Group of the Subcommission on Quaternary Stratigraphy of the International Commission on Stratigraphy is actually voting at this very time to decide on what will be the GSSP candidate that could potentially establish an Anthropocene epoch at the top of the geological timescale. So it is possible that within the next 12 months or so that we will leave the Holocene and be living in the Anthropocene. That's certainly a possibility. Really what I wanted to chat with you today about was what is the Anthropocene and what is causing it, how we might define the Anthropocene, and I want to show you specifically what the palaeontological signature of that is and how it's contributed to the definition of the Anthropocene. And at the end, I hope, if you'll forgive me, I want to come with a little bit of polemic about taking stock of our impact on the planet, and actually talk about the way in which I think paleontology has a very, very significant role to play from a societal perspective in terms of influencing the debate on what we do as we go forward as a species in the 21st century. So I'm going to begin then with the first question and just ask, what is the Anthropocene and what's causing it here? Because that's an important sub-question. And I'm going to begin with some figures that are probably very familiar to you, but which I feel are very important to start any presentation on with regards to the Anthropocene. So a few weeks back, I'm sure you all know that we passed another benchmark. There are now 8 billion Homo sapiens on this planet, and that's growing by around about 80 million of us each year. We increasingly live in huge structures. In the early part of this century, we became a predominantly urban species, and the projections are for the middle of the 21st century that over 2/3 of us will live in these large urban structures. And that's significant because urban environments consume something of the order of about 70% of the Earth's resources at present and contribute about 70% of human pollution. So if this figure is to grow and if our patterns of consumption are to continue at the level they are at present, that's going to have a very, very significant impact on the Earth system as we go forward into the middle and latter part of the 21st century. And those structures that we build are now commonly associated with trace fossil systems. I think the underground systems of London and other parts of the world are a really good signature of this rapid rate of development in the 20th and 21st century that will leave a permanent geological signal of humanity. I just want to compare ourselves with the other components of the biosphere. I started with this figure of 8 billion, and I find that actually quite difficult to visualize. I can't really think what 8 billion people looks like. I struggled to envisage what 14 million people might look like for the population of Greater London. But let's maybe compartmentalize that a little bit by thinking about some of our cousins. How many do they number? So our two closest relatives, of course, are the chimpanzee, about 250,000 specimens in the wild, and the beautiful bonobos with about 20,000 specimens in the wild. Okay, that's no more than the population of a single small human city like Leicester, the city I'm in at present, or Buffalo in New York. And I think this is a striking figure because you and I are more than 99.9% of the numerical abundance of all primates. And that is a remarkable figure for any representative of a group of organisms to be so dominant. Well, the Anthropocene is characterized by patterns of rapid change, and those that rapid change is particularly associated with the latter part of the 20th century. So here I'm showing you one of the graphs from Will Stephan, one of the members of the Anthropocene Working Group. And Will here is plotting a whole range of different parameters that are typical for the mid to late 20th century. You can see we've already talked about population, fertilizer consumption, water use. The one that always attracts people's attentions is the spread of McDonald's restaurants. There are 39,000 of them on the surface of this planet, and another 19,000 Burger Kings to add to that. In fact, that chain of restaurants alone would stretch from New York to Chicago if you were to line them up in a single row, which again, I think is a very interesting and important representation of our impact on the planet in the latter part of the 20th and 21st century. It's not just that. You and I as a species move more Earth than all of the rivers on planet Earth, and it's an order of magnitude greater, 316 gigatons of sediment, compared to about 22 gigatons of sediment by comparison for rivers. We use vast amounts of water. Again, I simply can't visualize what 4,000 cubic kilometers of fresh water looks like. So I thought of Lake Malawi in Africa, and that would be the equivalent of draining that lake every 2 years for our freshwater consumption, which is, you know, a ginormous pattern of consumption. We use vast amounts of energy. Again, of course, we all know this, and those projected energy levels will rise in the future. Much of this hopefully will be compensated for by more renewable sources of energy, but this is a pattern which will definitely grow as more and more of us live in cities. We put about 38 billion tons of carbon dioxide into the atmosphere in 2021, but perhaps the more significant figure there from an Anthropocene perspective is that 85% of all of our carbon dioxide emissions have happened since the 1950s. Again, a very good indicator of this accelerating process in the 20th and 21st centuries. And uniquely for any species in Earth history, and paleontologists out there tell me if I'm wrong, we dominate land and sea. We take tens of millions of tons of fish products from the oceans every year, and we waste something of the order of about 25% of those before they actually even get to market. Now, evidence of the scale of planetary change that I've tried to summarize to you there in those various figures is really evident if you look at the indication of changes in the nitrogen cycle at the surface of our planet as a result of the Haber-Bosch process, perhaps the greatest perturbation for 2.5 billion years. Of course, we know the rapid rise in carbon dioxide and the rapid rise in methane and its concomitant impact on the rise in global mean surface temperature. That's not everything that we could plot up for the Anthropocene. There's much more evidence of the scale of planetary change, and I hope to be able to show you some of that as we go through this talk. But perhaps the one to flag here is the 500 billion tons of concrete and the 8 billion tons of plastic produced since 1950. And that plastic is everywhere. Everywhere the Anthropocene Working Group has looked at sedimentary archives, we find plastics as an indicator of our increasing impact on this planet. Now, I want to focus very much on the changes that characterize the biosphere in the Anthropocene because, like you, I'm a paleontologist and it's the bit that I'm most interested in. So I guess I'd like to just summarize some of the big changes associated with the biosphere. 1 million species at risk of extinction, although of course we haven't documented anywhere near the global biodiversity of species on this planet at present. And if you Google extinct animals, of course, it's the big things that get noticed. The Caribbean monk seal, which has not been seen since 1952, the Yangtze dolphin that's not been seen since 2007. And then there's George, the Hawaiian tree snail, who really fascinates me because he went extinct on the 1st of January 2019. It's the end of his kind. And I want to come back to George, the Hawaiian tree snail, a little bit later because his demise is directly linked to human activities and particularly the translocation of the cannibal snail to the Hawaiian Islands in the middle of the 20th century. And George, of course, is part of a much bigger extinction event that we as paleontologists have been in the vanguard of trying to establish and document in the fossil record. Well, I'm not going to talk so much about extinction in this talk. It's most definitely a part of the Anthropocene, but my colleagues on the Anthropocene Working Group, like Tony Barnowski, could wax lyrical about this to much greater length than I could. But what I want to do is really explore just how truly unique our impact is on the Earth system and on the biosphere, because it is much greater than just extinction. We as a species have managed to halve the mass of the biosphere over the past 10,000 years, much of that as a result of deforestation. And we've concentrated mass in those things that we like to eat. Again, I think these are astonishing figures. We and our domesticated animals are 96% of the terrestrial mammal biomass, only 4% for the rest of wild mammals. We changed the landscape as well, and particularly dramatically over the past few centuries. This is the work of Earl Ellis, another member of the Anthropocene Working Group, and his work on anthromes, these human-modified ecosystems at the surface of the land on planet Earth. And just to really fast forward over 300 years, you can see just how dramatic the impact has been on the landscape over the past 300 years. And some more recent estimates have actually suggested that as much as 95% of the ice-free landscape at the surface of our planet is impacted in some way by humans. We converted half of the habitable land to farming and 3/4 of this for animals and dairy, again, with a significant wider impact on the biosphere. And we've profoundly changed the organisms within those ecosystems. This is what we've done to chickens over the past 70 years because we like eating them. We've changed their individual biomass fourfold. Oops. Oh, I missed a slide there, sorry. Just to emphasize that we eat something of the order of around 63 billion of these every year. And there are about 21 billion of them alive at any time on our planet. And again, likely to have left a very, very significant paleontological signal of these changes. We've begun to smear biogeographical boundaries, boundaries that were formative to our understanding of how this planet has evolved over long timeframes. This is a slide from one of my PhD students, Rachel Holmes, just plotting the distribution of golden apple snails through Southeast Asia. Golden apple snails, of course, are native to South America. What on earth are they doing in Southeast Asia? And of course, they have no regard for biogeographical boundaries. And Rachel's work now is actually quantifying the degree of homogenization of some of the elements of the biosphere in this part of East Asia. Invasive species are nearly everywhere at the surface of our planet. Again, this is a unique signature. We've seen interchanges of organisms in the past, for example, during the Great American Interchange, but now we're looking at an interchange which involves even the most remote parts of our planet. Now, of course, many of these changes have unfolded over several millennia. Humans have probably been translocating species for 20,000 years or so, but it's clear that many of these patterns have accelerated very rapidly into the 20th century. And I'm going to show you some clear paleontological evidence of that in a moment. The broiler chicken, for example, is one of these very clear patterns. This is some work we did with some archaeologists at Leicester a few years ago, led by one of my former PhD students, Caris Bennett, just looking at morphological changes in chicken bones since the archaeological record through to the 20th century. And it's a very, very significant change in the 20th century, as you can see there. Now, at this point, because I realize I've bombarded you with figures, and I apologize for that, but I think it's important in terms of clarifying what the Anthropocene is. I just want to step back for a moment and ask what is actually causing the Anthropocene? What is holding this edifice of change actually up? Because you might think it's you and me, as humans being the major driving force here. But another one of my colleagues on the Anthropocene Working Group, Peter Haff at Duke University, would argue that it's the technosphere, and that the technosphere is now driving this substantial change at the surface of our planet. And I think it's important for us to understand the technosphere if we're going to understand how we respond to these fundamental changes to the biosphere. What is the technosphere? In Peter's terms, it's an autonomous global system which comprises all of our technology, all of our social, political, military, agricultural systems. It's an emergent system. It's out of our direct control. We individually, we as nation states, we as a species have only limited control over its direction now. And it's colossal. The arterial systems of the technosphere are immense. Just look at the movement of commodities around our planet by the technosphere. It's everywhere. It's global and it's ubiquitous like other spheres. But unlike the other components of the Earth system that we know have co-evolved over a very long period of time to make a habitable space for life on planet Earth, the technosphere doesn't have that long history of co-evolution. In fact, in many ways, it's acting in a counter way to those other systems. It's predatory on them, it's parasitic. The problem for us is that without the technosphere, most of humanity couldn't exist. We need the technosphere to have this conversation this evening. We couldn't have it without the technology. And so the technosphere, like air, water, soil, and food, has become a necessity of human life. It's gigantic. This is a paper that my good friend Jan Zalazevich led a few years ago, just trying to quantify the mass of the technosphere. It's enormous. And one can use the idea of the technosphere as a vehicle which is accelerating and is out of control. It's something that Peter Hafer's used as an analogy, and I'm going to come back to that a little bit later in this talk. For the time being, I want to park the technosphere before the wheels fall off and go to the second part of this talk, which is more paleontological. And we'll actually ask how we might define the Anthropocene, and it will identify what role paleontology plays in this. So of course, this is the geological timescale that we're all very familiar with. It's a major contribution of geology to human knowledge. Here we have a framework of time which is essential for us to understand all of the processes that have unfolded as the Earth system has evolved through the enormity of geological time. And of course, we need this framework so that we understand each other when we're talking about this evolutionary timescale across the planet. And for that framework to be useful, of course, it means that those individual chronostratigraphical boundaries need to be defined as far as possible with a high degree of isochronicity. That is, we need to be as certain as far as possible that we're dealing with equivalent time everywhere on the planet. And that drives the process that we're using to think about defining the Anthropocene. Even though it's in a very recent time frame, we're still trying to use, obviously, the rules of stratigraphical nomenclature here. So I need to ask you the question, when did humans overwhelm the Earth system? And how is that represented in the geological record? And can we find evidence of that synchronous boundary that we can define? So there are three processes that I need to chat about with you. The first is hunting and gathering. The second one is landscape domestication. And the third one is globalization. Do any of these leave a signature that we can use to define the Anthropocene? Let's start with hunting and gathering. It goes back way into deep time, of course, but we can see some evidence, or some strong evidence, of our impacts on the biosphere from around about 50,000 years ago. We have a long history, of course. Hominins begin to make tools more than 3 million years ago. We leave a skeletal record that goes back nearly 3 million years. We become anatomically modern at least 300,000 years ago. We record signs of what appears to be very modern behavior. Some people have called cognitive fluidity. And around about the time, about 50,000 years ago, when there is widespread evidence for this increasing cultural complexity of humans, of course, we start to see patterns of impact of humans in the landscape, particularly in those landscapes where humans are the first human species. This is the time, of course, of the megafauna extinctions, which begin about 60,000 years ago and are continuing at present. And this may well be a product of both climate change and human impact, but it's clearly evident that in those regions where humans were the first human species in the landscape, the impact is much more considerable. It's not just manifested in the fossil record of the megafauna demise, but also of the associated changes to ecosystems. And that's left a very clear paleontological signal globally. Can't use it for defining the Anthropocene, though. Despite its profound impact on the biosphere and the fact that it leaves a very distinctive geological signal, it's not going to be useful from the perspective of defining a geological boundary, important as it still is in terms of our impact on the Earth system. What about landscape domestication then? Could we use that potentially to define the Anthropocene in the geological record? Again, there's clear evidence of landscape domestication and the spread of agriculture and pastoralism from about 13,000 years ago. And indeed evidence that trial cultivation was occurring in the Levant, in the Near East, perhaps as long ago as 23,000 years ago. So again, like hunting and gathering, its impact in the landscape and in the physical record is a gradual process unfolding over a long period of time. And of course, this is a multipolar process. It happens in lots of different places, independently, and as a result, the palaeontological record of cultivation, of agriculture, is also very different. It's defined by different taxa, different species in different places, and there's a high degree of diachroneity. So of course, it's of profound importance in terms of our impact on the planet. But again, these developments were strongly time transgressive. They're subject to reversal as a result of climate and environmental change. They can't be used to define a geological boundary, though nevertheless, they are of profound importance in terms of our ability eventually to have a major impact on the Earth's surface. What about globalization then? I'm going to take an arbitrary time of about 1500 CE, but also note, of course, that there was widespread inter-Indian Ocean exchange for a very long time, thousands of years before this, and also considerable interchange along the Silk Road. But 1500 CE is taken as the time of the Columbian exchange. It's taken as the time when the old world of Eurasia and the old world of the Americas were joined together for the first time, and consistently from then on to the present. So let's take that as our time frame for globalization. What about its paleontological signal? Because again, it's very distinctive. This is a figure from my colleague on the Anthropocene Working Group, Colin Waters, plotting up the spread of maize around the world, because maize is now one of the major cultivated crops by humans on the planet. Well, that's obviously left a very distinctive paleontological signal. You can find maize pollen in sediment cores from lakes in East Africa dating back to the 18th century. They're a very distinctive paleontological signal of the Columbian exchange. Here's another very interesting one for you. If you wanted to go and fish in the cesspit in Rembrandt's house, and from the 17th century, you probably wouldn't want to do that. I wouldn't want to do it either, but you might find clay pipes there. And in those clay pipes, you'd find tobacco pollen. So again, a distinctive indicator, a paleontological indicator of the Columbian exchange between the Americas and Eurasia. Of course, none of these early Columbian exchange signals are widely documented from the sedimentary record. They're all sporadic in their occurrence, and they do not, importantly, provide an isochronous set of markers. They're all time transgressive. So although, again, they're of profound importance for our understanding of how we as a species have become so dominant at the surface of this planet, they're not useful from a purely geological perspective of defining an isochronous geological boundary. What about the later stages of globalization, though? What about when we come forward to the 20th century? Can we start to recognize signatures then that do actually give us an indication of some degree of synchronicity? Indeed, we can, because as we come through into the 20th century, and earlier, of course, because this is a process which again has unfolded over a long period of time, we get evidence of the accelerating interchange of organisms across our planet, work that's been done with brilliance by Hannes Ebens and colleagues at the Senckenberg in Frankfurt. And that's left a very distinctive paleontological signature. This is something that we published as the Anthropocene Working Group in Palaeontology this year. I'm just trying to plot up some of those rapidly translocated species and trying to recognize their paleontological record in different sites, and noting that many of these species for the first time in the 20th century can be used to define with a high degree of precision paleontological chains of correlation that define these 20th century intervals when the Earth system was effectively overwhelmed by humans. Why is that important? It's important because this is the time in the 20th century when we start to homogenize ecosystems on this planet, not just natural at a rapid rate, but also human ecosystems. If you think about the biogeography of human culture, just summarized in this figure, the top left there is a 9th century Anglo-Saxon church near to where I live in Northamptonshire. And the bottom left is a 9th century temple in Vietnam. And on the right-hand side is 21st century London at the top. The bottom is 21st century Ho Chi Minh City in southern Vietnam. They're made from the same things, from glass and steel and plastic and concrete, materials that are traded globally and which have left a very, very distinctive signature of this accelerating impact of humanity on the surface of our planet in the 20th and 21st century. It's a global signal which dovetails with a isochronous record that we can find of radionuclides as a result of the mid-20th century atomic bomb blasts from the 1940s into the early 1960s. And this really is, of course, it's a terrible signature of humanity's impact on the planet, but it's just everywhere you look. This is a small lake just up the road from me, Groby Pool, and some great work done by a PhD student 3 decades ago now. And here you can see how Caroline David has plotted up the record of cesium in Groby Pool. And that first spike you can see there is almost certainly the spike from the 1950s, early 1960s bomb blasts. A really good marker of the Anthropocene, a really bad marker of our impacts on the planet, but one that we can recognize almost everywhere we look on this planet. And if you're wondering what the second spike there is, it's probably the impact of Chernobyl in the 1980s. And some of my PhD students are working very hard now to try and quantify the Anthropocene signature, biological and stratigraphical, in the local landscape of Leicestershire. Well, I hope I've demonstrated to you that by the time you get to the middle of the 20th century, it is possible by using a whole range of different markers to define an isochronous boundary. And that's important if you're going to then try to make a case to define a new epoch of Anthropocene geological time. Now, of course, that Anthropocene epoch, we would hope, would be to bracket the whole process of human evolution, to provide the framework, just as we have in the geological timescale, that enables us to speak the same language and understand these processes of change over long periods of time. What I wanted to show you now is just how granular this palaeontological signal is, because I've shown you kind of theoretical basis for this, but can you recognize this everywhere you look? If you go out into a lake nearby you, or you go into the sea, or you core a peat bog, can you find a fossil signature of the Anthropocene? Well, we can recognize evidence of that in the Leicestershire landscape, but I'm going to take you to San Francisco Bay. This is one of the sites that's been assessed as part of the study to try to define an Anthropocene geological boundary. You can see the other sites that we've looked at here. There are 12 sites across the planet. And I just want to show you what the paleontological signal of the Anthropocene is in San Francisco Bay, because it's very profound. In San Francisco Bay, something very dramatic has happened. We as a species have really re-engineered the biosphere in this part of the world, not just here, but indeed pretty much everywhere we're looking. How is that so? This is a rather remarkable website that you can go to if you want to watch the passage of international shipping across the surface of our planet. And it's as good an example as I can show you of just how the technosphere works. These are the global transport networks of international shipping, and they're responsible and have been responsible in the past for translocating numerous species across this planet with impunity. The technosphere doesn't care how it disrupts our ecosystems. Of course, one of the hubs on this international trade network is San Francisco. It's one of the busiest ports in the Pacific. And I want to show you the paleontological impact of the technosphere in San Francisco Bay and how that's clearly manifested in a changed ecosystem. So this is a groundbreaking study from the late 20th century that plotted up all of the introduced species into San Francisco Bay over the past 150 years or so. And we've now identified additional species that were not even known from observational records, but which have a clear paleontological signal. And I want you to note that half the introductions have occurred since the mid-20th century, so part of this accelerating trend. And the bottom right-hand comment there is also something which is really dramatic, I think. In some parts of San Francisco Bay, non-native species account for 97% of the total number of organisms and 99% of the biomass. So a very, very significant reconfiguration of this ecosystem. Let's have a look at the manila clam, because it arrives mid-century in 1946. It's quite typical of many of these introduced species that it becomes invasive. It proliferates in the bay, and in some places as many as 2,000 individuals per square metre, with concomitant impacts on the indigenous organisms. So we started a study with one of my PhD students, Stephen Himpson, working with the brilliant Mary McCann at the United States Geological Survey, who was really the first to recognise that microfauna could be used to identify the Anthropocene. And this is work based on more than 20, or based on 20 cores across San Francisco Bay, to try and work out what the biostratigraphical signature of the Anthropocene might be here. Some non-native species that have arrived in San Francisco Bay have a very distinctive biostratigraphical record across the bay. So here you're seeing ostracods that have been introduced from East Asia, from China and Japan. That's A and B. If you look at D at the bottom, you're looking at the foraminifera Trochamina haydai, also from the seas around Japan. And on the right-hand side is the Amur River clam from China, from East Asia. Again, what are all these organisms doing in San Francisco Bay? They've had a very significant impact on the ecology of San Francisco Bay. Again, this is Stephen's work. They arrive in 1986. You can see how rapidly the population increases to reach peak abundances of nearly 20,000 individuals per square metre in some parts of the bay after a few years. And its arrival had a very dramatic impact on the ecology here, because it's a prolific feeder which basically removed ecospace for other organisms in the ecology here. It's not the only one that's had a very significant impact. Trochamina haydai arrived from Japan in 1983. That's its observed record. Again, within a few years, it became the dominant benthic foraminifera in the bay, supplanting Elphidium excavatum, which had been a very dominant component of this ecosystem through the Holocene, and also previous records back in the Pleistocene. This is the level of detail that Stephen was able to develop through very diligent and hard work. This is one of Stephen's cores. It's going back to about 1952. It's got a very detailed age model based on a whole range of different parameters. I just want to show you how these different introduced species appear in the stratigraphical record. So the ostracods appear in 1975, around about when we think they would have arrived because of environmental reasons. And then above them, Trochamina haydai from Japan, this foraminifera. And then above them again, the Amur River clam in 1986. And the important thing to notice here is that the appearance of order of these species in the stratigraphical cores is the same as you would expect from a hypothetical reading from the time of introduction into San Francisco Bay. So we're able to replicate with very high precision the observational records in the stratigraphical record. And it's not just in one core. Stephen, because he worked brilliantly hard and did a fantastic job, here used ranking and scaling software to develop a biozonation across San Francisco Bay. This is a biozonation for about 2.5 meters of sediment from the past 70 years. And you can see that he was able to recognize 7 zones. So a very high resolution of zonation of this stratigraphical interval in San Francisco Bay. Not just recognizing the Anthropocene, but developing the kind of high resolution biozonation that we might use in the Silurian or the Jurassic, but here predicated only on the past 70 years. Well, that's San Francisco Bay. What do you do if you want to then correlate the Anthropocene around the planet, if you want to try to recognize this interval in the mid to late 20th century? Let's go across the ocean, 4,000 kilometers to Hawaii, to one of the most remote geographical regions on planet Earth. Remote though it is, it has a large number of introduced species. Those introductions have been taking place for a very long period of time. The Pacific rat, for example, was introduced to the Hawaiian Islands perhaps as long as 1,000 years ago, and has left a paleontological record of that introduction. And then more recently, invading snails have arrived on Kauai during the 20th century, the giant African snail. And then for good measure, and this is a classic one, I think, the cannibal snail was introduced to control the local populations of an expanding giant African snail. And the cannibal snail does exactly what it says on the tin. It eats other snails. And that had a dramatic impact on the indigenous snail fauna of the Hawaiian Islands. So here on Kauai, for example, some classical work from David Burney a couple of decades ago, plotting up the stratigraphical record of snails in the fossil record. Now you can see the indigenous snails at the bottom and the periods of human occupation shown on the right-hand side there. And then in the latter part of the 20th century, the indigenous snail population is extirpated and it is replaced by a fossil record of these introduced species. Again, a very distinctive paleontological signal of the Anthropocene. And I can't give you the details of this because it's been voted on at present, but I can tell you that many of the sites that we've looked at for the Anthropocene have a very distinctive paleontological signal that can be dovetailed with the other stratigraphical parameters and forms a very important part of trying to define this Anthropocene geological boundary from San Francisco Bay through Canada into Europe and into the Far East. There are very, very distinctive paleontological signals of the Anthropocene. So paleontology is a global marker of accelerating changes to the biosphere and of the Earth system. I hope I've been able to demonstrate that to you. And I've shown you one example, but I could show you many other examples of this too. I hope you'll forgive me at the end of this because I wanted to finish with a little bit of polemic, and I fear my voice is going a little bit, so just give me one moment. I just need to take some water. If you agree with the Anthropocene Working Group and with Peter Haff, who has been developing these ideas of the technosphere, that the technosphere of humanity and all of our social and technological interconnections is overwhelming the biosphere and indeed overwhelming the other components of the Earth system, then you can also very clearly see, I hope, from what I've shown you, that that technospheric impact, unique as it is in Earth history, is also leaving a very distinctive and unique fossil signal. The paleontological signal that we see as a result of this major change to the biosphere in the 20th and 21st century is quite different from any paleontological signal that I can think of in deep time, though I'd really be very happy if somebody could come up with something that they think is a similar comparison to this. And I think it's very important for us as geologists and paleontologists to be able to demonstrate these changes to the biosphere, that they are unprecedented, that they leave a fossil record that is unique and is identifiable nearly everywhere that we've looked on this planet, that it does show irreversible change because it is impossible to return San Francisco Bay and many other ecosystems on this planet back to their pre-human influence state. It also shows very distinctively an accelerating pattern of change, particularly accelerating in the 20th and 21st century. And I think that's really important, also from the perspective of the COP15 biodiversity meeting that's been going on in Montreal this week, that I'm sure many of you may have followed. Because really, as paleontologists, we know what's going to happen to the Earth system in the near future according to two different trajectories. We can predict that if it's business as usual, that our impact on the Earth system will be short-lived and unsustainable, and it will be marked by a mass extinction. We're already showing signs of entering that. It's a great marker for you and I. It's an appalling marker for humanity and also as our impact on the Earth system. The other possible route is that we develop a mutually beneficial relationship with the Earth system and its human technospheric component evolves and persists over geological timescales. That will leave a signal of ecosystem recovery, we hope, though those ecosystems will be fundamentally changed. And even in that scenario, I would argue to you that the changes are so significant that we've most definitely entered the Anthropocene epoch, a distinct change to global ecosystems and the biosphere, one with a profound and distinct manifestation in the fossil record. So by either measure, we are in the Anthropocene. Now that's important more broadly to society, because if we accept notions of the technosphere and its impact on the broader biosphere, it means that we need to challenge some of the notions of sustainability that are prevailing models at present. The idea, for example, that we can replace one form of consumption with another form of consumption, and that won't have damage or have a major impact on the Earth system around us. Because if we understand the technosphere properly, and I think it's a really important concept for trying to understand humanity's impact and the technosphere's impact more broadly on the Earth system, it means that even if supposedly sustainable, more consumption of a different kind may not stop the technosphere's voracious appetite for resources, or indeed its ability to degrade the biosphere. I told you this was going to be polemic. Indeed, we need human ecosystems that are more closely resembling those of natural ones. And I use this image of Max Painter because I thought it was topical at the present with the World Cup. It's rather challenging to get people to think of a football pitch perhaps as a viable ecology, but I hope you get the point that our knowledge of how the Earth system has changed means we need to be much more radical in the way in which we try to solve the problems of the technosphere and the degradation of the biosphere. Because we need to engineer, as Nick was talking about, we need to engineer places that are much more viable for the rest of the biosphere to survive in. And that's going to involve not just technological change, but also behavioral change at an individual basis. Peter Half often talks about us as individuals within the technosphere, and as individuals, we can also make a very significant impact collectively on changing the future trajectory. There are examples from history that show this. Tokugawa Japan, in the period when it was not accessible to the outside world, is definitely not a panacea. It was rigid and hierarchical and intolerant, but it was remarkably good for a very long period of time in developing a whole system of circular economies that were good at sustainability. Whole classes of artisans that mended pots and mended woodwork and pottery. And it managed to sustain itself over a long period of time by this kind of philosophy. So there are examples that we can learn from out there. I think that's important because if we can slow the pace of consumption, that might buy us some time. It might help us to guide the technosphere towards a more successful, mutually beneficial with the relationship with the biosphere. And who knows more about this than paleontologists? We're the ones who look at the fragments of the past biosphere to understand how it's cohabited with the broader Earth system. If I can finish then with this polemic, I think paleontology has a major role to play here. I've been lucky enough to be connected across a whole range of different multidisciplines over the past decade or so that I've been working on the Anthropocene. And they are really embracing of paleontology and what it can offer more broadly to a whole range of different disciplines, including the business community. I think that we, more than any other discipline, can demonstrate the accelerating patterns of the technosphere. And whether you believe that idea of Peter Half or not, we can definitely demonstrate the accelerating patterns of human impact on the Earth system through its Anthropocene fossil record. I think we can also highlight that paleontological signal is completely unique. I can't think of a paleontological signal in deep time that directly resonates with what we're seeing at present. I can see aspects of deep time changes that resonate, but I don't see anything as unique as what is happening at present. And I think, therefore, we have a major role to play in influencing the discussion on how we change the behavior of the technosphere or humanity's interaction with the Earth system, which can play a role in the future well-being of planet Earth. So that's all I wanted to say, and I'm very grateful for the opportunity to be able to say that. Thank you very much for listening.